Have you ever just stopped to really wonder what unseen forces are actually holding molecules together, shaping them, making them twist and turn just so?
Mm.
Or maybe why some chemical reactions just roar to life while others barely whisper, even when, the molecular players look surprisingly similar.
Yeah, it's a fundamental puzzle, isn't it? Underpins everything in chemistry.
It really does. And today we're going to dive deep into exactly that.
Getting right to the heart of molecular behavior, understanding that hidden language of electrons and bonds that truly dictates everything.
Welcome to the Deep Dive, the show where we take your source material and distill it into clear, engaging, and, well, often surprising insights. I'm your host, ready to unpack some seriously fascinating science.
And I'm happy to be here. It's always exciting to pull back the curtain on this intricate molecular world with you.
Okay, let's get into it. Our mission for this deep dive is to explore the very foundations of how molecules are built and how they react.
The real nuts and bolts.
Exactly. We're drawing our insights from one of the absolute giants in the field, Chapter 1, Chemical Bonding and Molecular Structure, from Advanced Organic Chemistry, Part A, Structure and Mechanisms, 5th edition by Carey and Sundberg.
A classic text, really foundational.
Our goal is simple. Clearly explain core structures, reaction mechanisms, key concepts. Make these ideas come alive. We'll even touch on the experimental and computational tools that, bring these insights into focus.
So you'll gain a really profound understanding of the language and logic behind organic chemistry.
Exactly. This chapter really does set the stage for predicting how molecules will interact.
Which is absolutely critical, whether you're trying to understand existing processes or design new ones, maybe in medicine or materials science.
And here's why you should care about, say, the nuances of electron distribution or molecular orbital theory.
Yeah, why wade into the details?
Because understanding these foundational principles is honestly a direct shortcut. It helps you predict chemical behavior, design new compounds, and really see the elegance behind synthesis and analysis.
In pharmaceuticals, biotechnology, you name it.
Get ready for some serious aha moments, because this knowledge, it isn't just theoretical, it's intensely practical.
Okay, let's dive in.
So, let's kick things off where many of us started our chemistry journey. Valence bond concepts, VB theory.
Right. This is kind of the bedrock, isn't it? Where our understanding of molecular structure really began.
Introductory organic chemistry often starts here with the Lewis approach.
And VB theory really built on that in the 19th century. It was crucial for figuring out structural formulas, recognizing functional groups. Think Hückel's benzene structure back in 1865.
Wow. So the way we draw bonds today owes a lot to that early work.
Absolutely. And the core idea of a VB bond is, well, pretty intuitive. It's about electron pair bonds.
Right.
At its heart, VB theory says when atoms bond, you get this concentration of electron density right between them.
Good.
This pileup of electrons leads to a stable, low-energy state at a specific distance between the nuclei.
Or like in the hydrogen molecule, H2.
Perfect example. The simplest one. The two electron clouds merge. Density builds up right in the middle between the two protons.
And the diagrams show this really clearly, right?
Yeah, the figures in the book show that accumulation beautifully. And just as importantly, you see electron density depleted outside the nuclei. It emphasizes that the electrons are really focused on that bonding job in the middle.
That visual really helps.
Mm-hmm.
Okay, so from that basic idea, we get to one of the most powerful concepts taught in Intro Chem. Hybridization.
Hybridization. sp3, sp2, sp. It comes from this theoretical mixing of atomic orbitals, the s and p orbitals we all know.
To form new blended hybrid orbitals.
Exactly. And it's a brilliant way for us to describe how atoms arrange their electron clouds to get the best possible bonding geometry.
So for an sp3 carbon, like in methane, that's the classic tetrahedron, right?
Yeah.
109.5 degree angles.
Textbook example.
But what about ammonia, NH3, or water, H2O? They're often described as P32, but the angles are slightly smaller. Ammonia is around 107.3, water is 104.5. Why the pinch?
That slight difference is actually super insightful. It tells us about electron repulsion. Those unshared electron pairs, lone pairs on nitrogen or oxygen, they essentially occupy orbitals that are a bit bigger, more spread out than the bonding pairs.
Okay, so they take up more space.
Effectively, yeah. Which means they push back a little harder against the bonding electrons, causing slightly greater electron repulsion. This squeezes the bonding pairs closer together, reducing the angle. It's subtle, but it really shapes the molecule.
And hybridization isn't just for single bonds, is it? It's key for double and triple bonds, too.
Oh, absolutely. sp2 and sp hybridization are essential there. You still have sigma bonds, the strong head-on overlap of hybrid orbitals.
Right.
But now you also get pi bonds. These come from the sideways overlap of the unhybridized orbitals that are left over.
And those pi bonds are different. They have that nodal plane.
Exactly. A flat plane right through the bond axis where there's zero electron density. The electrons are above and below that plane. And because the sideways overlap isn't as good as head-on, pi bonds are generally weaker than sigma bonds.
That sigma versus pi distinction is just so vital for visualizing things like ethene.
Ethene, with its sp2 carbons, is perfect. It's planar, flat, which maximizes that orbital overlap for the pi bond.
Makes sense.
Then you get something like alene, with that central spur carbon. It needs to form two pi bonds.
Right.
So to make room, the two outer CH2 groups have to twist 90 degrees relative to each other. It's a direct consequence of needing two perpendicular pi systems on that central carbon.
Okay, here's something the source really emphasized, and it was a bit of an aha moment for me. We talk about hybridization like it's something an atom chooses to do, but the book stresses. Hybridization describes the geometry we observe. It doesn't cause it.
That is a truly crucial distinction. Often gets glossed over. Molecules don't sort of decide, okay, time to hybridize sp3 and then become tetrahedral.
Right.
Instead, they naturally find the geometry, the shape that maximizes the good bonding interactions and minimizes all the repulsions, electron repulsion included. Hybridization is our model, our framework, to understand and explain that optimized shape we see. It's a powerful descriptive tool.
A lens, not a blueprint.
Yeah.
Got it. Speaking of electron repulsion, that reminds me of the O2 molecule. Oxygen.
Yes, diatomic oxygen.
If we just draw a simple double bond, Lewis structure style, you'd think all the electrons would be paired up.
Seems logical.
But O2 is paramagnetic, has two unpaired electrons. How does VB theory, or maybe the Pauli principle, handle that? Seems counterintuitive.
It's a classic case where fundamental principles lead to surprising results. The Pauli exclusion principle basically says electrons, especially those with the same spin, really want to stay apart. Occupied orbitals need maximum separation.
Okay.
So for O2, if you distribute the electrons to achieve this maximum separation while still forming a double bond overall, the lowest energy arrangement actually ends up with two unpaired electrons.
Huh. So it's balance.
It's a balance between getting strong bonding and minimizing electron repulsion. It satisfies the octet rule for both oxygens and correctly predicts the paramagnetism. It just shows how seriously electrons avoid each other.
Okay, from arranging electrons, let's talk about sharing them unequally. Electronegativity and polarity. Linus Pauli's definition is just so elegant, isn't it? The power of an atom in a molecule to attract electrons to itself.
It really is. And that power is deeply tied to where an atom sits on the periodic table.
Right, across a row.
Across a row, say lithium to fluorine, the nucleus gets more positive, higher effective nuclear charge. It pulls harder on the electrons. Even though you're adding electrons, the inner shells don't screen that extra charge perfectly. So fluorine's outer electrons feel a much stronger pull than lithium's. Electronegativity increases.
And down a group, like fluorine down to iodine.
Going down, the valence electrons are in shells further from the nucleus. They're also shielded by more layers of inner electrons.
So they're held less tightly.
Exactly. So electronegativity decreases. It's also linked to atomic size atoms generally get smaller across a row and bigger down a group.
The source mentions a bunch of different numerical scales for electronegativity. Ullered-Rochow, Lewis-Benson, Mulliken, spectroscopic. Why so many? What's the takeaway?
Yeah, it shows it's a complex property. Each scale looks at it slightly differently, deriving it from different physical measurements or calculations. Ullered-Rochow uses effective nuclear charge and radius. Lewis-Benson, valence electrons and radius.
The Mulliken averages ionization potential and electron affinity.
Right, and that one's interesting because it actually finds strong theoretical support later in density functional theory, which we'll get to. The spectroscopic scale even lets you measure it experimentally.
So don't sweat the exact numbers.
Pretty much. Focus on the trends and the implications. They all tell a similar story about which atoms pull electrons harder.
Okay, so what is the big implication? What does different electronegativity do in a molecule?
The biggest thing is polar covalent bonds. Unequal sharing leads to partial positive and negative charges on the atoms. Think BF3, CF4, NF3.
Right.
In BF3 and CF4, the individual BF or CF bonds are super polar, but the molecules themselves, zero overall dipole moment.
Because they're symmetrical, the poles cancel out.
Exactly. Trigonal planar for BF3, tetrahedral for CF4, perfect symmetry. But NF3 is pyramidal. It does have a net dipole moment about 0.235 dB. Small but distinct positive and negative ends.
And electronegative groups can affect the whole molecule, right, like inductive effects.
Yeah, absolutely. Look at acyl trifluoroacetate. Those highly electronegative fluorines and oxygens pull electron density towards them, inducing significant partial positive charges on nearby carbons, making them targets for nucleophiles.
That leads to this idea of electronegativity equalization, doesn't it? It's not just isolated bonds.
Precisely. When atoms with different electronegativity bond, the electron density shifts around the entire molecule until, effectively, the electronegativity is equalized everywhere. It's the basis for understanding how a group far away can influence a reaction site, those polar substituent effects.
Like a ripple effect through the bonds.
Yeah, that's a good way to think of it. These inductive effects propagate, subtly changing reactivity down the chain.
Now, carbon itself, our favorite organic chemistry element, doesn't have one fixed electronegativity either, does it? It changes with hybridization. That was surprising to me.
That's a really key point. And supply hybridized carbon is more electronegative than sp2, which is more electronegative than sp3.
Why is that?
It's all about the ses character in the hybrid orbital. S orbitals are closer to the nucleus, more penetrating than p orbitals. So electrons in an orbital with more stes character are held more tightly.
Ah, so spin has 50% character, sp2 has 33%, sp3 only 25%.
Exactly. More S character means the nucleus pulls those electrons in more strongly, making the carbon effectively more electronegative. All the different numerical scales mentioned in the source confirm this trend. sp3, sp2, sp.
And this directly impacts reactivity.
Hugely. Look at the acidity of carboxylic acids. Propanoic acid, sp3 carbon group attached, pKa 4.87. Propanoic acid, sp2 group, pKa 4.25, more acidic. Propanoic acid, sp group, pKa 1.84, much more acidic.
Wow, that's a big jump.
It's a direct result of the increasing electronegativity of the carbon group pulling electron density away, stabilizing the negative charge left behind when the proton leaves, making it easier to remove.
You even see it in strained rings?
Yeah, like cyclopropane. Its CH bonds are unusually acidic because the CC bonds have more P character to accommodate the strain, forcing the CH bonds to have more S character.
Right.
We can even assign electronegativity values to whole groups like methyl, ethyl, vinyl, ethanol. Very useful for predictions.
Okay, so electronegativity is about holding electrons tightly. What about how easily their clouds can be distorted? That gets us to polarizability, hardness, and softness.
Right. Polarizability is how easily an atom's or molecule's electron cloud gets deformed by an external electric field, maybe from an approaching ion or polar molecule.
And bigger atoms are more polarizable.
Generally, yes. Larger atoms or ions, especially those further down the periodic table, have more diffuse electron clouds that are less tightly held and further from the nucleus. They're easier to distort. We call them softer. The source has a table showing this trend clearly.
It's directional, too.
It can be. In methyl halides, for instance, the electron cloud distorts more easily along the CX bond axis. This concept is linked to things like refractive index and how nonpolar molecules can have temporary induced dipoles.
Which brings us to Pearson's hard-soft acid-base theory, HSA. Always like this one.
It's a really powerful qualitative tool for predicting reaction preferences. Hardness, eta, and softness, sigma, are formally defined using ionization potential and electron affinity, similar to Mulliken electronegativity.
So what makes something hard or soft?
Generally, hard species are small, highly charged, not easily polarizable. Think F-ion or H+ers. Soft species are larger, maybe less charged, or even neutral, and easily polarizable, like I-ion or a neutral benzene molecule. Hardness tends to increase with electronegativity and positive charge.
And the core principle, the predictor.
Principle of maximum hardness. Basically, hard acids prefer to react with hard bases, and soft acids prefer to react with soft bases. Like Seeks-like.
What's the difference in interaction?
Hard interactions are mostly electrostatic strong attraction between opposite charges. Think ionic bonds. Soft interactions are more about mutual polarization, and covalent bonding, the electron clouds, distort and overlap significantly to form a bond. This helps predict which potential reaction partners are favored.
How does this relate to electron transfer in a reaction?
Electronegativity and hardness together dictate how much electron transfer occurs. Take halogens reacting with methyl radicals. Fluorine is very hard and electronegative, so you get almost complete electron transfer, forming a very polar, almost ionic CF bond. Iodine is much softer, less electronegative, so the electron transfer is less complete. The Ci bond is more covalent. More about that mutual polarization.
Okay, next big concept, resonance and conjugation. This really ties a lot of organic chemistry together, explaining molecules that one Lewis structure just can't capture.
Absolutely. Resonance uses multiple Lewis structures connected by that double-headed arrow to represent a single real molecule, which is actually a hybrid or weighted average of those contributing forms.
Benzene being the classic
The
example.
classic. It's two equivalent Kekulé structures average out to give the hexagonal geometry and the intermediate bond lengths, 1.40, that we actually observe. It's not flipping back and forth, it is the average.
And resonance means extra stability, doesn't it? It's not just a drawing trick.
Crucially, yes, resonance, stabilization, or delocalization energy. The real molecule is more stable than any single contributing Lewis structure would suggest.
Why? What's the origin of that stability?
It comes down to reducing electron repulsion. By spreading the pi electrons out over a larger part of the molecule, delocalizing them, you lower the overall energy. Think of it like spreading charge out.
Less crowding.
Exactly. The pi electron density in benzene is beautifully uniform around the whole ring, unlike in a non-cyclic molecule like 1305 hexatrine, where it's more bunched up in the double bonds. That even spread is stabilizing. The source shows electron density maps. Comparing them, it's very clear.
Okay, quick refresher. Rules for drawing valid resonance structures.
Sure. 1. Only electrons move, never atoms. The nuclear positions stay fixed. 2. Don't violate the octet rule, or duet for hydrogen. Each atom needs its maximum valence electrons, keeps things chemically sensible.
So if resonance means electrons are delocalized, that's what happens in conjugated systems, like 1,4,3 butadiene.
Precisely. Conjugation means alternating double and single bonds, which allows for continuous overlap of orbitals along that chain. Electrons can delocalize across it, leading to stabilization.
How much in butadiene?
In 1,3 butadiene, resonance suggests some increased electron density between C2 and C3, maybe implying some double bond character there. The charged resonance forms are less important, though. The source indicates the effect is modest, a slight stabilization.
But in something like copanyl-acrylane resonance, has a much bigger impact on reactivity, right? This is where it gets really practical.
Propanol is a fantastic example. You have the main uncharged structure, but also two charged ones. The one with negative charge on the electronegative oxygen is way more important than the one with negative charge on carbon.
Okay.
This unequal contribution skews the electron distribution. It puts partial positive charges on C1, the carbonyl carbon, and C3, the beta carbon.
And that dictates how it reacts.
Totally. The C-key double bond becomes less reactive to electrophiles, but that beta carbon, C3, becomes highly susceptible to attack by nucleophiles. When a nucleophile adds there, you form a stabilized, delocalized anion. This is why alpha, beta unsaturated carbonyls are such versatile building blocks in synthesis.
The effect of the substituent really shines through, like in methoxyethene or ethenamine.
Excellent examples. An alkoxy group, OCH3, or an amino group, NH2, directly on a double bond acts as a powerful electron donor through resonance. Nitrogen's lone pair is even better at donating than oxygen's.
Making vinylamine super reactive.
Exactly. This electron release pumps electron density into the double bond, especially onto the beta carbon, making it incredibly reactive towards electrophiles. The cation formed when vinylamine gets protonated, for instance, is stabilized by a whopping 80 kilocomble compared to a simple methyl cation. That's huge. It explains their synthetic utility perfectly.
So the big takeaway on resonance, it's a powerful predictive tool. It shows you how functional groups change the electron map, highlighting reactive spots.
Precisely. It guides our intuition about where reactions are likely to happen, like an electron roadmap.
Now let's shift slightly to hyperconjugation. This isn't about pi bonds interacting, is it? It involves sigma bonds.
That's right. Hyperconjugation is the interaction of electron density from a sigma bond, usually a CH or CC bond, with an adjacent empty or partially filled p orbital, or, more subtly, with an adjacent antibonding sigma star orbital.
So sigma electrons getting involved in delocalization.
In a way, yes. It's a weaker form of delocalization than resonance, but it's still significant. For example, oxygen or nitrogen substituents can weaken adjacent CH bonds through this effect. If a CH bond is lined up just right, antiparaplanar to a nitrogen lone pair, that CH bond actually gets longer and weaker. You can sometimes see this experimentally.
So there's a geometry requirement, a stereoelectronic component.
Absolutely critical. The interaction is strongest when the donor orbital, the sigma bond or lone pair, is aligned perfectly anti-paraplanar 180 degrees apart to the acceptor orbital, the p orbital or sigma star. Maximum overlap equals maximum stabilization or interaction. This controls subtle conformational preferences and can dictate reaction pathways.
Before we jump fully into the quantum world, let's quickly cover atomic size. Covalent and van der Waals radii. Why do we need both?
Good question. Covalent radii are based on measured bond lengths. They give you an idea of an atom's effective size when it's sharing electrons in a chemical bond. Pauling had an early scale. Others like Slater and Alcock refined them, especially for organic chemistry.
Yeah, and this...
They generally get smaller across a row, more nuclear pull, and larger down a group, more electron shells. The source has tables showing this.
Okay, and van der Waals radii.
These define the minimum distance between atoms that aren't bonded to each other. Think of it as an atom's personal space in a crowd of molecules, like in a crystal or liquid. They're derived from how closely atoms pack together in solids.
So they're bigger than covalent radii.
Generally, yes. They represent the outer boundary of the electron cloud for non-bonded interactions. Both are crucial covalent for bond lengths, van der Waals, for understanding intermolecular forces, packing, enzyme substrate interactions, that kind of thing.
Great. That sets us up perfectly for the next big section, molecular orbital theory, MO theory. Moving beyond localized bonds to electrons roaming the whole molecule.
Indeed. This is a shift in perspective. Unlike VB theories focus on electron pairs between two atoms, MO theory treats electrons as belonging to the entire molecule. They occupy delocalized molecular orbitals that can span all the atoms.
More holistic.
Exactly. The molecule's properties arise from the sum of contributions from all these orbitals, filled and empty.
And it all starts with the Schrödinger equation.
Fundamentally, yes. In practice, we often use the linear combination of atomic orbitals, or LCAO, approach. Molecular orbitals are built mathematically by combining the atomic orbitals of the constituent atoms.
How does the calculation actually work?
It's usually an iterative process. You start with a guess for the geometry and electron distribution, calculate the energy, then refine the geometry and the self-consistent field, how the electrons interact with each other, and the nuclei over and over until you find the lowest energy state.
And the output gives us?
Precise atomic positions, the energy of each molecular orbital, and coefficients telling you how much each original atomic orbital contributes to each new molecular orbital. Lots of detailed info.
Let's start with a simpler version. The Hückel MO method, HMO. Good for pi systems.
It's a brilliant simplification, specifically for conjugated pi systems. It makes some big assumptions. Pi electrons are treated separately from sigma electrons, and only adjacent p orbitals interact.
Key terms: Coulomb and resonance integrals.
Right. The Coulomb integral, alpha, is like the baseline energy of an electron in an isolated p orbital. The resonance integral, beta, represents the energy change, the stabilization, when adjacent p orbitals overlap and interact.
What does HMO give us?
It generates the energy levels for the pi molecular orbitals and the coefficients showing how the atomic p orbitals combine to make each MO. The source has diagrams showing the MOs for linear polyenes, like hexatrine, highlighting the nodes regions of zero electron density. More nodes means higher energy.
And this leads to the really crucial idea of frontier orbitals.
Yes. The HOMO, highest occupied molecular orbital, and the LUMO, lowest unoccupied molecular orbital. They're called frontier because they're at the energetic edge.
Most accessible for reactions.
Exactly. The HOMO holds the highest energy, most easily donated electrons, crucial for reactions with electrophiles. The LUMO is the lowest energy empty orbital, the most accessible place to accept electrons, crucial for reactions with nucleophiles. Their energies and shapes are key predictors of reactivity.
But HMO has limits, right? Especially regarding stabilization energies?
It does. It's great for relative energies and symmetries in pi systems, but it often overestimates delocalization energy, especially for cyclic systems like benzene. Benzene's real stabilization is about 30 kilocalmol, much more than simple HMO predicts compared to hexatrine, so you use it qualitatively more than quantitatively for energy.
But it led to Hückel's rule for aromaticity. That's huge.
Absolutely. A powerful rule derived from HMO insights. It states that planar, fully conjugated rings are aromatic specially stabilized if they have 4n+2 pi electrons, N0, 1, 2.
Like benzene with 6 pi electrons and 1.
The archetypal example. And systems with 4n pi electrons, like cyclobutadiene, 4-cyclooctatadiene, 8, are anti-aromatic, often destabilized and reactive. The rule also works beautifully for ions, like the aromatic cyclopropenyl cation 2-pi and cyclopentadiene anion 6-pi. Extremely useful rule.
So HMO is a simplified start. How did MO methods get more accurate?
We moved to semi-empirical methods, things like extended Hückel, CNDO, MNDO, and more modern versions like AM1 and PM3.
How are they better?
Key improvement. They include all valence electrons, sigma and pi. They still use approximations, but they also incorporate empirical parameters values fine-tuned against experimental data or higher-level calculations.
So a mix of theory and experiment.
Kind of. They give more complete information, geometry, coefficients, orbital energies, offering a better picture than basic HMO. Good balance of speed and accuracy for many systems.
And for the highest accuracy, from first principles calculations, ab initio methods.
Exactly. Ab initio from the beginning. These methods are derived directly from quantum mechanics. No empirical fudge factors. The common starting point is the Hartree-Fock approximation.
Using basis sets.
Right. Mathematical functions, usually Gaussian functions, that describe the atomic orbitals. You have different sizes and complexities. STO3G is minimal, then 321G, 631G, 6311G. Bigger sets generally mean more accuracy, but also more computational cost.
And how well do they match reality?
Often remarkably well. For molecular structures, bond lengths are typically predicted very accurately, within hundredths of an angstrom. Energies, like heats of formation, are also usually good, though highly strained molecules can still be tricky.
Can they handle solvents?
Yes, that's important. We can use continuum models like PCM that treat the solvent as a continuous medium with a certain dielectric constant. This helps account for how the solvent environment affects structure and energy, especially crucial for ions.
Let's visualize these MOs. Methane, CH4. What does MO theory say?
Methane's tetrahedral symmetry dictates its MOs. You get one low-energy bonding MO covering all atoms, and then 3 degenerate same-energy bonding MOs that have a bit more p character and nodes at the carbon. The source shows these.
Is there experimental proof?
Yep. Photoelectron spectroscopy, like ASCI, measures the energies needed to kick electrons out. For methane, it shows 2 distinct ionization energies for the valence electrons, matching the prediction of 2 different MO energy levels. Pretty neat confirmation.
What about ethene, the double bond?
Ethene is planar, lots of symmetry. The most famous MOs are the pi and pi star orbitals, made from the carbon p's s orbitals sticking perpendicular to the molecular plane.
The ones involved in the double bond.
Exactly. Then all the other orbitals, H1, C2, C2px, C2 pi, combine within the molecular plane to form a set of sigma MOs, handling the CC and CH single bonds. It's a bit more complex, various combinations.
Are there simple rules to guess MO energies?
Qualitatively, yes. More nodes generally means higher energy. And sigma interactions, head-on overlap, are usually stronger than pi interactions, sideways overlap. So the energy gap between bonding and anti-bonding is typically larger than between pi and pi.
The source has pictures of these.
Yes, computed energy level diagrams and pictorial representations showing the shapes and nodes of ethene's MOs. Understanding the symmetry of these orbitals is really important, especially for predicting outcomes in certain types of reactions, like paracyclic reactions.
Okay, that brings us to a super useful application. Perturbational MO theory, PMO, and frontier orbitals. This is where the theory directly predicts reactivity.
Right. These bridge the gap between abstract MOs and what actually happens in the flask. PMO theory helps us understand how small changes to a molecule, like adding a substituent, perturb its MOs and thus change its reactivity. It simplifies the analysis.
And the frontier orbital concept is central.
Absolutely. The core idea. The most important interactions in a reaction happen between the HOMO of one molecule, the electron donor, and the ALUMO of the other, the electron acceptor.
Because they're closest in energy.
Exactly. Closest energy gap means strongest interaction, most stabilization when they mix. And crucially, they also need compatible symmetry to overlap effectively and form bonds. This tells you where molecules are most likely to react.
Let's use that classic comparison. Ethene versus formaldehyde. Both have double bonds, but react so differently. Why?
Perfect illustration of frontier orbital control. Formaldehyde's CO bond loves reacting with nucleophiles. Ethene's CC bond doesn't really, but ethene CCC is much more reactive towards electrophiles than formaldehyde's CO.
And the MO theory explains this difference.
Beautifully. Oxygen is much more electronegative than carbon. In formaldehyde, this pulls the electrons in the CO bond strongly towards oxygen, lowering the energy of both the pi, HOMO-like, and pi star, LUMO orbitals compared to ethene.
So formaldehyde's LUMO is lower, making it a better acceptor.
Exactly. Its low-energy pi star, LUMO-MO, readily accepts electrons from nucleophiles. Ithene's pi orbital, HOMO, is higher in energy, making its electrons easier to donate to electrophiles.
And the charge distribution matters too.
Yes. In formaldehyde's pi MO, more density is on oxygen, leaving the carbon electron deficient, partially positive, which also attracts nucleophiles. The source has diagrams showing these energy differences in orbital shapes. The closer the HOMO and LUMO energies, the stronger the interaction.
So electrophiles go for ethene's HOMO, nucleophiles for formaldehyde's LUMO. It clicks.
Precisely. The diagrams show this clearly. Ethene is poised to donate from its HOMO. Formaldehyde is poised to accept into its LUMO. It matches observed reactivity perfectly.
How do substituents change this? Adding an amino group to ethene versus, say, a formal group.
Good examples. Pi donors like amino, NH2, or alkoxy, OCH3, push electrons in. They raise the energy of the pi HOMO, making it an even better donor, and increase electron density, especially at the beta carbon. So much more reactive towards electrophiles at that beta carbon. Enamines are prime examples.
And pi acceptors, like the formal group in propanol.
They pull electrons out. They lower the energy of both the pi and pi star orbitals. The LUMO becomes a better acceptor, and electron density is pulled away from the beta carbon, making it electron deficient, electrophilic. So reactivity shifts towards nucleophilic attack at the beta carbon. Very predictable effects.
Orbital symmetry isn't just for simple cases, right? It explains more complex reactions too, like concerted reactions.
Absolutely. Why doesn't an allycation just add cleanly across ethene to form a cyclopentalocation in one step? Symmetry mismatch. The symmetry of ethene's HOMO doesn't align properly with the symmetry of the allylation's LUMO for bonding to happen at both ends simultaneously in a concerted fashion. The interaction at one end would be bonding, the other anti-bonding, they'd cancel out. Prevents that specific pathway.
And ozonolysis, that multi-step cleavage.
Classic example. It proceeds via cycloaddition, then cycloreversion, then another cycloaddition. Each step is concerted and requires orbital symmetry matching. The first step, ozone adding to ethene, works because ethene's HOMO has the right symmetry to interact productively with ozone's LUMO. Symmetry rules dictate feasibility.
What's the connection between Mo-Frontier orbital theory and HSAB theory? Is there one?
Yes, a very neat one. Hard interactions usually involve a large HOMO-LUMO gap. Orbital interaction is weak. Electrostatics, charge attraction, dominate. Soft interactions typically have a small HOMO-LUMO gap. Now, orbital interaction, that perturbational stabilization from mixing HOMO and LUMO, becomes much more important, often dominating over simple electrostatics. Covalent bonding character is key. So frontier orbital theory provides the quantum mechanical basis for the empirical HSAB rules.
Moving beyond qualitative predictions, MO theory can also give impressive numerical results.
Yes, often excellent agreement with experiment. Bond lengths are usually predicted very well, even with modest methods. Heats of formation are generally good for standard molecules, maybe less so for very strained ones. Molecular dipoles tend to be slightly overestimated, but the trends are usually correct.
What about something complex like acidity in water, pK values?
That's a tough test involving ions and strong solvation effects. But yes, MO calculations, especially when combined with thermodynamic cycles that estimate solvation energies, can predict relative aqueous acidities quite well, as shown for carboxylic acids in the source. It demonstrates the power of these methods even for complex solution phase phenomena.
So MO theory, from simple Hückel to complex ab initio, is a really versatile toolkit.
Absolutely. Visualizing orbitals, understanding energies, predicting reactivity, it gives us deep insights, like chemical X-ray vision.
Now, let's switch gears slightly to density functional theory, DFT. This really shook things up in computational chemistry in the 90s. What's the big idea?
DFT was revolutionary because it shifted focus. Instead of calculating individual wave functions and orbitals for every electron, DFT focuses on the total electron density of the entire system.
Just the density.
Yes. The cornerstone is the Hohenberg-Kohn theorem, which proves that the ground state energy of a system is uniquely determined by its electron density. All the complex information about electron correlation, how electrons interact and avoid each other, is somehow implicitly contained within that density.
Totally different approach.
Completely. In practice, we use the Kohn-Sham equations. The tricky part, the part where approximations come in, is the exchange correlation functional, which tries to capture those complex electron interactions based on the density.
B3LYP is a common one. Very common. It's a hybrid functional, meaning it mixes different theoretical approaches for exchange and correlation.
What's the practical advantage of DFT?
Often is computational efficiency. DFT calculations can be significantly faster than high-level ab initio methods for systems of similar size, making it possible to study much larger molecules, big organic structures, organometallics, even parts of enzymes.
And it gives similar outputs, geometry, energy.
Yes, minimum energy, geometry, total energy, and properties related to electron distribution, like dipoles.
How accurate is it? Bond lengths, energies?
Generally very good. Bond lengths are often predicted extremely accurately within 0.1A for CC bonds. CH bonds might be slightly off, but predictably so. Gas phase acidities, ionization enthalpies, DFT correlates very well with experimental data for many types of molecules.
And it connects back to concepts like electronegativity. Yes, fundamentally. DFT provides a rigorous theoretical grounding for concepts like electronegativity, related to how energy changes when you remove electrons, and hardness, softness, related to the curvature of that energy change. It validates those qualitative ideas.
Okay, if DFT is all about electron density, how do we visualize it?
Good question. Total electron density is a real measurable quantity. You can get it from X-ray crystallography. But often we look at deformation density. You compare the actual measured or calculated density to a theoretical density you'd get if you just placed neutral spherical atoms at the nuclear positions. The difference shows you where density builds up in bonds, lone pairs, and where it's depleted due to chemical bonding.
So for benzene, what does it show?
Density contours show that nice uniform electron distribution around the ring. Deformation maps clearly show density accumulating between the carbon atoms, the CC bonds, and around the CH bonds, and depletion in the center of the ring and further out. Visual proof of delocalization.
And formaldehyde.
Total density is higher around the electronegative oxygen, as expected. The deformation map highlights buildup in the CH bonds, the CO bonding region shifted towards oxygen, and importantly, in the regions corresponding to oxygen's lone pairs. Very informative picture.
Beyond pictures, how do we assign numbers, like atomic charges, from these calculations?
There are different schemes. Mulliken population analysis, MPA, is one older method. It divides up orbital overlaps. The exact numbers depend heavily on the calculation details, so you focus on trends.
Like how electrons shift.
Exactly. Qualitative redistribution.
What about natural bond orbitals, NBO, and natural population analysis, NPA?
NBO is neat because it tries to find orbitals that correspond closely to our Lewis structure concepts, localized bonds, lone pairs. NPA then assigns charges based on these natural orbitals. It often gives charges that align well with chemical intuition.
Like positive hydrogens even in methane.
Sometimes, yeah. NTA charges can reveal subtle shifts, like electron density moving towards electronegative substituents. NBO can also dissect bonding energy into localized Lewis-like and delocalized resonance hyperconjugation contributions.
Then there's Bader's atoms in molecules, AM theory. Sounds very fundamental. Defining atoms within the molecule.
That's the goal. AM uses the topology of the electron density itself. It finds paths of maximum electron density between nuclei arete. These are the bond paths. Along each path, there's a point of minimum density called the bond critical point.
Okay.
The surfaces where the gradient of the density points downhill away from these critical points define the boundaries between atoms. It partitions the molecule's electron density into distinct atomic basins.
So it carves up the electron cloud based on its own shape.
Precisely. The molecular graphs in the source for alkanes show how AIM rigorously divides them into methyl and methylene units, supporting the idea of group contributions to properties. You can see density peaks at nuclei, ridges along bond paths, and the saddle point at the critical point.
Can AIM tell us about pi character, ellipticity?
Yes. Ellipticity measures how much the density at the bond critical point deviates from being perfectly round, cylindrically symmetric. A higher ellipticity indicates more pi character. Ethene's triple bond is cylindrical, zero ellipticity. Ethene and benzene show significant ellipticity. It can even pick up subtle effects like hyperconjugation.
And electronegativity. Does the critical point move?
It does. It shifts along the bond path towards the more electronegative atom. The tables in the source show this clearly for bonds to hydrogen and in substituted methanes. It's a quantitative measure reflecting that electron pull.
AIM sounds like it could give surprising insights into reactive intermediates.
Definitely. Take the methyldiazonium ion, CH3N2 plus AI. AIM shows a very weak CN bond and a high positive charge on the methyl group. It looks almost like a methylcation loosely attached to N2, explaining its extreme instability. Comparing it to the ethyl version reveals stability trends related to carbocation stability.
What about methoxide ion, CH3O?
We know it's a strong base nucleophile because of the high negative charge on oxygen. But amine analysis also highlights significant negative charge on the hydrogens. This suggests it might have potential, maybe unexpectedly, to act as a hydride donor in some situations. Interesting nuance.
So AMA, MPA, NPA. They all give different numbers for atomic charges. What gives?
That's the crucial takeaway. Atomic charge is not a uniquely defined physical observable. It depends on how you choose to partition the electron density. The source shows this for formaldehyde. Different methods, different numbers.
So focus on the trends, not the absolute values.
Exactly. All the methods generally agree on the direction of electron shifts, which is what's chemically most important for understanding polarity and reactivity.
Can charge analysis explain something like a Mathayed resonance?
Amides are perfect. Their properties, polarity, protonation on oxygen, not nitrogen, the rotational barrier around the C-N bond, around 18 kilomole, scream resonance. NPA analysis confirms the charge transfer from nitrogen to oxygen consistent with that partial double bond character in explaining the barrier.
Lastly, electrostatic potential surfaces, EPS. These seem very visual.
They are. EPS maps the electrostatic potential, the energy a positive test charge would feel, onto the molecule's electron density surface. It's theoretically meaningful and experimentally accessible, usually color-coded. Red for negative potential, electron-rich. Blue for positive potential, electron-poor.
And they directly predict reactivity.
Very intuitively. Electrophiles are attracted to the red negative regions. Nucleophiles are attracted to the blue positive regions. It shows you the molecule's electrostatic face to the world.
Like for substituted ethans.
Yeah, the source shows how electron donors make the potential near the double bond more negative and shift it towards the beta carbon, Markovnikov attack. Electron withdrawers make it less negative or even positive, directing nucleophiles. It's a great visual predictor.
Okay, we've covered a ton of ground on the fundamentals. Let's dive deeper into some specific topics from the chapter, applying these ideas. First, topic 1.1, the rotational barrier in ethane. Seems simple, but the why is complex.
Right. Ethane prefers the staggered conformation over eclipsed by about 2.9 kilokimol. A small barrier, but fundamental to the shapes of alkanes and everything else.
What causes it? Simple bumping of hydrogens.
Not really. Van der Waals repulsions are too small. It's more about destabilizing factors in the eclipsed form, mainly repulsion between the electrons in the CH bonds on adjacent carbons. Both electrostatic and quantum mechanical Pauli-exclusion repulsion.
But what stabilizes the staggered form?
The dominant stabilizing factor is thought to be hyperconjugation, sigma delocalization. The CH sigma bonding orbitals on one carbon align optimally with the CH sigma star antibonding orbitals on the next carbon in the staggered conformation.
Ah, that sigma star interaction again.
Exactly. It allows a tiny bit of electron delocalization, which lowers the energy. NPA analysis confirms that this hyperconjugation, along with minimizing exchange repulsion, are the key factors favoring staggered.
Does the barrier change if you swap CC for CN or CO?
Yes, predictably. As the bond gets shorter, ethane to methylamine to methanol, the barrier decreases regularly, 2.9, 2.0, 1.1 kilocoulomb. The electronic factors change subtly with the atoms involved.
That leads nicely into topic 1.2. Heteroatom hyperconjugation or the anomeric effect. Hyperconjugation on steroids.
Kind of. It's enhanced hyperconjugation when you have a heteroatom, like O or N, with a lone pair next to a bond that can accept electrons into its sigma star orbital. Think lone pair donating into an adjacent antibonding orbital.
And sigma interaction.
Precisely. You can even draw a no-bond resonance structure to represent it. It stabilizes the molecule by lowering the energy of the lone pair electrons as they partially populate the sigma star.
And it requires specific geometry.
Crucially, yes. The interaction is strongest when the lone pair orbital is anti-periplanar, 180 degrees, to the acceptor sigma star bond. This alignment preference is the origin of the anomeric effect in sugars, and it dictates conformations in acyclic systems too.
Which bonds are good acceptors?
Sigma star acceptorability increases with electronegativity of the atom in the bond. CFCO-CNCC. And also, interestingly, down a group for halogens, CIC, BRC, CLCF, likely due to lower sigma star energies. Donorability also varies.
Examples?
Dimethoxymethane prefers a gauche-gauche conformation, not the extended anti-anti, because gauche allows optimal N-sigma overlap between each oxygen's lone pair and the other CO bond's sigma star, worth 5 and 7 kilomole. Fluoromethanol prefers gauche for similar reasons, oxygen lone pair anti to the CF bond, worth about 5 kilomole. Similar effects in fluoromethylamines.
So this stabilizes the molecule, But the source says alpha halo ethers and alkenes are super reactive. Seems paradoxical.
It's a key point. The N-sigma interaction does stabilize the ground state conformation, but it also weakens the CX carbon-halogen or similar bond involved in that interaction.
Oh, making it easier to break.
Exactly. That's why these compounds undergo solvolysis incredibly fast in polar solvents. Methoxymethyl chloride reacts maybe 10^14 times faster than methyl chloride. The hyperconjugation pre-weakens the bond, facilitating its departure to form a stabilized conjugation. Internal stability coupled with enhanced reactivity at that specific bond.
Let's tackle topic 1.3. Bonding in small rings, especially cyclopropane. Strain energy.
Right. Rings like cyclopropane are forced into non-ideal bond angles, 60 degrees versus 109. This stores strain energy, making them less stable and often more reactive than open-chain analogs. Reactions that open the ring relieve strain.
How does VB theory explain the bonding? Bent bonds.
That's the classic VB picture. To make 60-degree angles, the sp3 hybrid orbitals can't point directly at each other. They overlap off-axis, forming weaker bent or banana bonds that arc outwards.
And rehybridization happens?
Yes. To accommodate this bending, the CC bonds take on more p character. P orbitals prefer smaller angles than sp3. Consequently, the CH bonds must take on more s character. This matches observations. Short, strong CH bonds and open HCH angles in cyclopropane.
What about the MO perspective?
MO theory offers a different view. Imagine combining 3 sp2 hybridized CH2 groups. The remaining p orbitals overlap 2 sideways, one head-on-ish inside the ring to form the CC framework. You get a unique set of delocalized sigma MOs, one particularly stable one inside the ring. It has some sigma aromatic character.
How much strain energy, and where does it go?
Total strain is about 40 kilomole, but those strong CH bonds actually provide about 8 kilomole of stabilization. And the sigma delocalization adds another 11 kilomole of stability. There's even evidence for a ring current in NMR. The Laplacian plots also show unique density buildup in the ring center.
What about even more strained rings? Bicyclo 1.1.0 butane, propellant.
Bicyclo 1.1.0 butane is super strained, 64 kilomole. The central CCC bond is almost pure p character, high energy HOMO, very reactive towards electrophiles, undergoes unusual ring openings.
And 1.1.1 propelling, the stability paradox.
Right. It's incredibly strained, but surprisingly resistant to thermal decomposition compared to larger propellants. Why? Breaking the central bond homolytically is very energy costly and doesn't release as much strain as you might think. Kinetically stable to that specific pathway.
But still reactive otherwise.
Oh, yes. That central bridgehead bond is highly reactive towards other reagents, thiols, halogens, polymerization. The strain makes those rehybridized orbitals eager to react, just not necessarily by falling apart thermally. Strain channels reactivity.
Fascinating stuff. Topic 1.4. Using the Laplacian function to represent electron density, seeing bonds and lone pairs.
The Laplacian measures the curvature of the electron density. Where it's negative, L and A star is positive, density is locally concentrated. Where it's positive, L is negative, density is depleted. It's great for visualizing features.
What features?
It clearly shows maxima corresponding to electron concentration in bonding regions. Even more strikingly, it shows distinct maxima for non-bonding electron pairs, like the lone pairs on oxygen and water or nitrogen and ammonia. The source has great pictures for methane, ammonia, water, ethane, ethene showing this. You literally see the lone pairs.
Like a match experiment.
Beautifully. The source shows computed versus experimental Laplacian plots for ethane. The agreement is excellent, validating the calculations.
How does it show electronegativity?
It clearly maps the density shifts. Comparing N2, symmetric, with CO, density shifted towards C, surprisingly. And formaldehyde, density clearly pulled towards O in the CO bond and concentrated in O lone pairs. Powerful visualization tool.
Okay, final topic, 1.5. Applying DFT concepts to chemical properties and reactivity, tying it all together.
Exactly. DFT provides a rigorous quantitative framework for many of the qualitative VB and MO concepts we rely on.
Like defining electronegativity and hardness softness mathematically.
Yes. DFT defines chemical potential as the negative of Mulliken electronegativity, related to how energy changes with electron count. Hardness is related to the curvature of that energy change, how resistant the potential is to change. These DFT definitions correlate well with empirical scales and provide a basis for HSAB and the principle of maximum hardness. Even covalent and van der Waals radii can be defined theoretically within DFT using density contours.
And DFT has its own reactivity predictor, the Fukui function.
Right. The Fukui function describes how the electron density at a particular point changes when the total number of electrons changes, i.e. upon oxidation or reduction. It tells you where the density is most sensitive to adding or removing an electron.
So, like frontier orbitals, but based on density changes.
Exactly. You can calculate F plus, sensitivity to adding an electron where a nucleophile attacks, and F, sensitivity to removing an electron where an electrophile attacks. Local softness combines this with the overall molecular softness. For formaldehyde, the Fukui functions pinpoint carbon as the site for nucleophilic attack, high F+, and oxygen for electrophilic interaction, high F, matching MO predictions but derived purely from density.
How does DFT explain substituent effects?
It provides a theoretical foundation. Substituents alter reactivity by changing the electron density distribution through both inherent polarity, electronegativity differences, and polarizability, hardness, softness. DFT can calculate group electronegativities and hardness values.
Like for alkyl groups or unsaturated groups?
Yes, it confirms sp2, sp3 carbon electronegativity. Interestingly, it often finds methyl to be slightly more electronegative and harder than ethyl, especially in the gas phase, due to polarizability effects. Subtle but important details.
Can it explain tricky acidity trends, like gas phase versus solution?
Yes. The increasing acidity of hydrides across rows and down groups correlates well with the DFT electronegativity and hardness. The famous reversal of alcohol acidity, methanol to butanol in water, but opposite in gas phase, is explained by polarizability in DFT-HSAB terms. Softer, larger alkoxides, like T-butoxide, better stabilize the charge in the gas phase. Solvation flips the order.
And halogenated alcohols.
Another great example, gas phase order, ClCH2OH, BrCH2OH, FCH2OH, reflects the competition between electronegativity, favors F, and polarizability, favors BrCl. Polarizability wins out in stabilizing the resulting anion in the gas phase. DFT captures these competing effects.
Wow, what an incredible journey through the fundamentals. From VB's bent bonds and resonance to MO theory's orbitals and symmetry, and DFT's focus on electron density. We've really unpacked the core principle.
We really have, seeing how hybridization, electronegativity, frontier orbitals, hardness, softness, how all these concepts, whether qualitative or quantitative, help us predict and understand how atoms connect and react. It moves us beyond just knowing what happens to understanding why.
So for you listening, you now have a much firmer grasp on the core structures, the mechanisms, even the computational tools that chemists use constantly. This deep dive really is a shortcut to getting truly well-informed.
It gives you insights that go beyond just facts, explaining the underlying logic of chemical behavior. And this foundation is key to understanding so much more drug design, materials science, biology.
Just think about it. These microscopic interactions, this dance of electrons and nuclei, it underpins everything. The medicines we take, the fuels we burn, the materials of the future, it all starts here.
The principles we talked about today are the bedrock for all that innovation.
So what other molecular mysteries would you explore with this deeper understanding?
The possibilities really open up once you grasp this fundamental language.
Thank you so much for joining us on this deep dive into the heart of organic chemistry structure and bonding. We hope you enjoyed gaining a deeper appreciation for the sheer beauty and logic of it all.
It's been a pleasure exploring it with you.
Until next time, keep learning, keep questioning, and stay curious.